Good morning, guys. This is a follow-up video on notes for a two-sampled z-test as opposed to building a confidence interval to estimate a population parameter. Now we're going to do a test, a statistical significance test, to support or not support a claim. So we have the main ideas here for doing any sort of significance test, and that is that we want to know what inference procedure to use. We want to decide between estimating with a confidence interval and doing a significance test. So you would use a two-sample z-test for the difference in populations when you're comparing categorical data, and you have two random samples drawn from two different populations, and they're drawn independently, so the sample from one population does not affect the results of the other population. Okay, so categorical data, for example, they either experienced nausea or they did not. They graduated from college or they did not. They got first place in the Tour de France or they did not. They biked for a team in the Tour de France or they did not. They climbed a mountain or they did not. Okay, so that's sort of categorical data and comparing two populations. And then number two, like all hypothesis tests, we state a null and alternative hypotheses, and we define the parameters. The proportion of all people in the population who got headaches. Okay, population 1, population 2. Also, like all hypothesis tests, number 3, we identify the significance level, or the alpha level. If it's not stated, it's 0.05. Like all statistical inference procedures, we identify the conditions or requirements. We make sure it meets the requirements, and we'll go through those. Like all hypothesis tests, we use a test statistic. Okay, remember the test statistic is a z-score. The number of standard errors that a sample statistic differs from the parameter, and that will get us to the p-value. And in the case of a difference of two proportions, we are doing a test, we're doing the number of standard deviations that the difference of two proportions is from the true difference. And number 6, again, we use a p-value to determine whether or not we should reject or fail to reject the null hypothesis. And then we state if there is or is not convincing evidence to support the claim based on rejection or not rejection of the null, which is based on whether the p-value is high or low in relation to the alpha level. Okay, let's check out an example from the World Almanac. So we're comparing two populations here. The population of college students who were women. It looks like it's from all college students. And the two different populations are two different time frames in this case, the year 2000 and the year 2018. And we're wondering if there's actually a significant difference in the number of college students that were women in those 2 years. So how do we find that out? We take samples. We probably can do this as an observational study. We don't need to run an experiment. We just look at the data from 2000 and 2018, and we choose 1,481 random college students from 2000, and it turns out that 809 were women. And in the year 2018, we chose 1,977 randomly, and 1,120 were women. So it's hard to tell immediately if there truly is a difference in these two proportions. So that's why we would do a statistical test to determine if it's significant or not. Is there evidence to support the claim that there has been a change from 2000 to 2018? Okay, so we would use a z-test, a two-proportion z-test, because these are two random samples drawn from independent populations. and we're talking about categorical data here, the number of college students that were women. We state our parameters. P sub 1 is the proportion of female college students in 2000, and P sub 2 is the same proportion in 2018. We state our null and our alternative hypotheses. The null hypothesis is that the difference in the population proportions is 0. In other words, we are going to assume that there is no difference between these two years in the proportion of college students who are women. We make that assumption so that we can provide an alternative hypothesis that we can test if it's statistically different from the null. And that alternative hypothesis is simply the year 2000's proportion minus the year 2018's proportion is not equal to 0. There must be some difference then. If the probability of the difference in our sample statistics is low, the probability of the difference happening by chance is low. So that's what we're after. No significance level given, we'll use 0.05. And now we check the requirements. Random sampling, yes. We'll have to assume that we had a pretty large supply of college students, at least 10 times greater than our sample. And we can make that assumption. There's a lot more than 14,000 and 19,000 college students in those years. And then to use the normal distribution to approximate or model this situation, we have to make sure that our number of successes and failures in both samples is greater than 10. And there's no problem there. We had a pretty large number that were women and a pretty large number that were not women, well more than 10. Okay. Now, something that's a little different here with the differences in sample proportions versus a single population is that if we assume the null is true, that the two population proportions are equal, and there's no difference between the year 2000 and the year 2018 in terms of the number of college students that were women, we can just put our two samples together. We can pretend they're coming from the same population. So the 809 out of 1481, we'll combine it with the 1120 out of 1977. So we're essentially combining our successes and we're combining our sample sizes. AP uses the notation P sub C hat for combined sample proportions. Your book uses P bar. So I will put a little note there. This is also P bar. You might see it as P bar. Okay, so that's what we're going to use for our P hat, essentially. That is our point estimate, or our best estimate at the true proportion of college students who are women. Okay, something got messed up in the copy here, but all of this is just checking the requirement that we have 10 successes and 10 failures. That should go up here. And we do have that. So moving on, we're going to find a test statistic, just like we did with a single proportion, or a single population. Okay, we have our two P hats, sample 1, sample 2. If we subtract those two, the difference between the year 2000 and the year 2018, that's 2000, that's 2018, not a bad idea to label those, is negative, which means we had a higher proportion of women in 2018 from our sample of 1977 that were women. So the difference in those two proportions is negative 0.021. Okay, so that allows us to calculate our test statistic. What do we need? We need the standard deviation, because we want to divide that difference by the standard deviation of the difference in sample proportions, or the standard error of the proportion, and that'll give us a z-score. How many standard deviations is that difference? Okay, you'll see it, this is written a little differently here, but essentially we're using the same formula. Remember, the difference, the standard deviation of the difference in sample proportions is going to be p hat times q hat divided by n. But remember, we have two proportions here, so we have to find the standard error for both sets and add them. When we're finding a difference for the standard deviation, remember, we always add. And the key here is that we're using the pooled proportion. Remember, we got 0.558 for our p sub c hat, or p bar, or pooled proportion. And that's shown here. And 1 minus our p sub c hat is 0.442. That's the same for both proportions. When we pool our sample proportions, then the numerators of both fractions are going to be the same. So we could have written this as 0.558 times 0.442 over 1481 plus 0.558 times 0.442, pardon the bad writing, over 1977 square rooted. This just factors out the 0.558 times 0.442, since that is common to both of those terms. That leaves a 1 in both numerators, and so it would turn into this. Same thing algebraically. So either way, we get for a standard error 0.017, how far we would expect to deviate on average from the 0.558. So that's essentially your numerator and your denominator. We've got the difference in our sample statistics. We've got our standard error. We do the division, and we get a z-score of negative 1.24. Okay, good idea to draw a picture here. Negative 1.25 standard deviations below the mean here-ish. Okay, back to the null hypothesis real quick. Okay, this is not equal to, so this is a two-tailed test, remember? We're just testing if there is a change in the number of college students who are female, so I actually want to go to 1.24 as well, and I'm interested in both tails. This is a two-tailed test. These are our critical regions. What's the probability that we would be at least that extreme in both directions? And that's done with a normal CDF. And you'll see here it's being doubled because it's two-tailed. And we used a lower bound of 1.24. You could have used an upper bound of negative 1.24 and a lower bound of negative 100 as well. Either way, you'd get half of this. This is already doubled since it's 2 times. So that's your p-value. That's a probability value. The probability that you would land in either one of those tails. It's pretty high. It's 21.5%, way higher than the alpha level of 0.05, which means it's not that unlikely that the difference in those 2 years would have happened by chance. The difference in those 2 samples could very well have happened by chance, just sampling variation. So the conclusion is that we fail to reject the null hypothesis. We don't have convincing evidence that there is a difference between the years 2000 and 2018. based on those two samples, on the number of college students who were women. Okay, let's move on here. This problem is straight from the text, and we're going to do it with the graphing calculator. So we're going to kind of speed through this one. We have a randomized control trial in Kenya. Insecticide-treated bed nets were tested as a way to reduce malaria. Okay, so this is an experimental design. And we're going to have one group that was, we had bed nets treated with insecticide, and we had another group where there were no bed nets used. So either they developed malaria or they did not develop malaria, and the two groups are bed nets and no bed nets. As far as testing a claim, you can see here in the last sentence, second to last sentence, it says the significance level and test the claim. So when you're choosing the inference procedure, you're going to use a z-test, a significance test, and since we have two different groups, we're going to do a two-proportion z-significance test. Do bed nets appear to be effective? Well, we're going to have to get a p-value and decide for ourselves. So I always like to think initially, does there appear to be a difference just by looking at the two samples? It looks like 343 infants who used bed nets, out of those 343, 15 developed malaria. Slightly smaller sample of infants who did not use bed nets, and more, almost twice as many, developed malaria. So we do have evidence that there is possibly a difference, or it's more effective to use a bed net in terms of developing malaria. The question is there significant or convincing evidence of such? And that's why we do the test. Okay, important to state the parameters. Parameter 1, or P1, is the proportion of infants who used bed nets and developed malaria. Proportion 2 is a proportion of infants who did not use bed nets and developed malaria. We state our null and our alternative. Boy, that's hard to say. Our alternative hypothesis. And as is typically the case with a difference of two proportions, the null hypothesis is that there is no difference in the two proportions. We assume that truth to start. And in this case, I want to go back to the wording here. Yeah, all it asks, test the claim that the incidence of malaria is lower. Oh, I guess it stated it pretty definitively there. The incidence of malaria is lower for infants using bed nets. Okay, so you do have to be careful here, and this is why it's important to state your parameters, because which one are we subtracting? Which one is the way we're subtracting going to result in a positive or a negative number, depending on our alternative hypothesis? So if P1 is bed nets, and P2 is no bed nets, we would like that, if we subtract bed nets minus no bed nets, we're hoping that's going to be a negative number, because there'd be fewer infants who develop malaria if they used bed nets than there would be if they didn't. So we're going to hopefully get evidence that P1 minus P2, bed nets minus no bed nets, is less than 0, is negative. Okay? State the alpha level, 0.01. It means we need a really small p-value, less than 1%. Check your requirements. We do have random assignment. In this case, it's an experiment, so random assignment to two groups. Let's check our normal distribution requirements, and that is that successes and failures in both samples greater than 10. We've got that here. And since in our null hypothesis, we are assuming that both populations are equal in terms of the number of infants who developed malaria, we can pool our sample proportions. And that's what's happening there. So this is our true point estimate, or our best guess at the true proportion of infants who develop malaria, about 6.5%. Okay, the rest of it, nice and easy with the calculator, as long as you know what you're putting in and what's coming out. We're going to go to stat, over to tests, down to a two-proportion z-test. I think that's number 6. Let me just verify that for you. It is number 6. And the menu asks you to identify X1, N1, X2, N2, and the direction of our alternative hypothesis. And that's it. It does the rest for you. So X1 is the number of successes in the first sample. N1 is the sample size of the first sample. Number of successes, and by successes I mean infants who develop malaria. Not the best terminology there, but you know what I mean. The sample size for the second sample. And then this is a one-tailed test to the left of our test statistic. Let's see, I'll put all that in now. Yep. And we get a test statistic, or a z-score, of negative 2.439, which you might realize immediately is pretty low. And it also calculates a p-value for you. We don't have to do a normal CDF. It does it for us. And we do end up being lower than 0.01. And since that probability of getting at least as extreme a value of negative 2.439 is low, then we do say there is convincing evidence that the true proportion of all infants using bed nets who develop malaria is lower than the true proportion of all infants not using bed nets who develop malaria. We reject the null. All right, I hope that helps, guys. Any questions, get in touch. Have a great weekend.